Hi, and welcome back to another class of physics. This will probably be our last and final video, and we're going to cover nuclear physics in this video. Here we have the definitions of radiation and radioactivity. It's important to know that some atoms are unstable and are radioactive. And as a nucleus tries to achieve stability, radiation is given off. So radiation is a general term for energy emitted from radioactive substances. And radioactivity is a spontaneous emission of these radiation from the nucleus of an atom. Remember that with nuclear reactions, everything happens in the nucleus. So how is a nuclear reaction different from a chemical reaction? Well, as we stated earlier, a nuclear reaction takes place within the nucleus of an atom, whereas chemical reactions result from the interactions of electrons. So as you can see in the illustration to the right, the nucleus is made up of those green and yellow particles, whereas the electrons would be on those outer rings. So how do we go about naming a nucleus or an element? We're going to start off with hydrogen, and this is an exception to the rule because hydrogen is the only element that does not have any neutrons. Now, as we look at naming nucleuses, there's two boxes on the left. The one on the bottom, the atomic number, indicates your number of protons. That will never change, as the atomic number, or your number of protons, is essentially the fingerprint or the DNA of an element. So for hydrogen, there's only one proton in the nucleus. Right on top of it, in that second box, in the top left corner, we have the mass number of these elements, or the nucleuses. And in there would be the proton plus the number of neutrons. Now, like I said, hydrogen is the only one that does not have any neutrons. Therefore, the atomic number and the mass number for hydrogen is 1. For every other element, these will change. What will always remain the same, though, is your atomic number or your protons. At some point, you've heard of isotopes. Isotopes of an element have the same number of protons, but different number of neutrons. So if you've seen the periodic table of elements, the most common version of the element is always listed in that table. And by that, we mean that the most common format of the mass number. So what characteristics do isotopes of the same element share? That is their atomic number and chemistry. Remember that the atomic number is equal to their number of protons, which is basically their DNA. What characteristics do the isotopes of the same element do not share is that their atomic mass, their radioactivity, and their nuclear physics. So the atomic mass can vary, and when it does, that's an isotope. Now, isotopes have the same atomic number and different atomic mass. Isotopes will have similar or identical chemistry, but isotopes will have different nuclear behavior. So here we take a look at carbon. Of course, the most common format of carbon is the one with the mass of 12. At all times, the atomic number, or the protons for a carbon, is 6. So we have carbon 13 and carbon 14, one that you may have heard plenty of times about. We have nuclear reactions. We have a nuclear decay, which is a spontaneous process in which an unstable nucleus ejects particle and changes to another nucleus. This is part of alpha decay and beta decay. More of this information later. And we have also fission and fusion. Fission is when a nucleus splits into two fragments of roughly equal size, and fusion is when two nuclei combine to form another nucleus. So two small ones combine to create a bigger one. We'll come back to all of these later. So we have 3 different types of nuclear radiation: alpha, beta, and gamma. Their composition is listed. Most of the ones that we deal with are going to be your alpha and beta. Your symbols are there. Now, with their mass, the mass of alpha is 4, and the electric charge of this is 2. Now, this leads us to be the element of helium. Remember that the 2 is the atomic number. So there's 2 protons, and it has 2 neutrons for a total of 4 in mass. As we look at beta, beta does not have any mass, or if it does, it's very small. And the electron charge of that is a -1. Now with gamma radiation, again, you have absolutely no mass there and no charge either. Now when we look at their penetrating powers, You don't need to have the rank from lowest to highest. Alpha is the lowest, gamma is the highest, and the amount of shielding that needed from them also varies. So if their penetrating power is very low, like alpha, you don't need a whole lot. For example, paper or wood or even clothing or even a piece of cloth is enough to prevent penetration. Whereas with beta, you're going to need a little bit more thicker with aluminum or other metals. And with gamma, you're going to need lead, as the penetrating power of gamma is very high. Let's look at alpha decay, which is a nucleus ejects an alpha particle, which is basically your helium nucleus. You'll see reactions occur. Now, as we said, alpha decay can only occur with heavy elements. In this case, we are seeing a spontaneous reaction or a spontaneous alpha decay of the 239 plutonium nucleus. Now, remember that the helium is essentially two protons and 2 neutrons given a mass of 4. And the atomic number of that would be 2 for the 2 protons. So when the plutonium goes under alpha decay, as we'll see with the helium on the right-hand side, the end result is that we now have a 235 uranium. The uranium, of course, 92 indicates that we're at the uranium, and the 235 indicates that that is the mass of the atomic number, the amount of neutrons plus the amount of protons added together. Now let's move on to a sample problem. I know in this slide it already gives you the answer, but let's go ahead and pretend that those numbers on the right-hand side didn't exist. So complete the reaction of the alpha decay for thorium-232. So the 232 indicates for us that that is the atomic mass. That's what goes on the top left box of the thorium. Of course, thorium has an atomic number of 90. Now we're going alpha decay, which means that it's a helium, and we're looking at a mass of 4 and atomic number of 2 for helium. So treat that arrow as if it was an equal sign, and what you're trying to figure out is what element would occur on the right. And the way to do that is you take that 232 and you subtract 4, so you get 228 for a mass, and you take the 90 minus the 2 to get you an 88. Once we have the 88, we know that's the atomic number, and 88 protons would give us radium. So the trick with any of these is to make sure that the top row numbers always add up to the one that you see on the left, and the bottom row numbers always add up to the numbers that you see to the left as well. Moving on to beta decay. A beta particle is when a negative electron is released. Beta decay occurs when a nucleus has too many neutrons for protons to be present, and a neutron converts to a proton. So we have carbon-14. Now remember that the most common one is carbon-12, but carbon-14 over here, and it goes under beta decay. Now beta means that it's a 0 with a negative 1, and the symbol for that is, of course, an electron. So again, if we treat that arrow as an equal sign, and we take a 6 minus a negative 1, that becomes a positive 1. So that's basically 7. So now we know our element is of the 7th one, has 7 protons, which is nitrogen, and the mass of that will remain as 14 because the beta decay does not have any mass. So the mass of that is 0. So 0 plus 14 will still remain as 14. Going on to gamma radiation. Gamma radiation is going to be electromagnetic in nature, and gamma rays have basically no charge and are the most penetrating of all rays. This is why you need the most amount of protection from them. As dangerous as they are, they have very practical applications. For example, you could do radioactive dating of fossils. You've heard of carbon-14 or carbon dating. You have medical treatments of cancer with gamma ray lasers and radioactive implants and tumors. And you also get medical diagnosis of organ failures and tracheias. Anytime you go on for x-rays and so on, you have that as well. So although they seem very dangerous, with the right amount of protection, they can be safe. Moving on to nuclear fission and fusion. Fission occurs when an unstable heavy nucleus splits apart into 2 lighter nuclei, forming 2 new elements. Fission can be introduced by free neutrons, and mass is destroyed and energy is produced according to the Einstein equation of E equals mc squared. With fusion, it occurs when 2 light nuclei come together to form a new nucleus of an element. This is going to be a new element in its own. Fusion is the most energetic of all nuclear reactions, and energy is produced by fusion in the sun. So that's the most prime example of it. And fusion of light elements can result in non-radioactive wastes. So as we look here, we have one hydrogen added to another hydrogen, which is two smaller nuclei, two lighter nuclei coming together, and they form a bigger one, which is going to be helium. All right, Einstein's famous equation. Energy released when a nucleus is formed from nucleons. It is very high binding energy, which is going to result into a stable nucleus. And, we talk about mass defect, but in this class, we're just going to focus and use mass of the object. So E equals mc squared is going to be equation number 50 in our formula sheet. E, of course, is energy. Any kind of energy is going to have units of joules. Mass, just like anything else, we need to be in kilograms. And C is the speed of light, 3 times 10 to the 8th meters per second. And that is a constant in your formula sheet. So let's go ahead and do a sample problem. It says, what is the maximum possible energy released from 175 grams of thorium? So obviously we're looking for energy. We don't know what that value is, but we know it's going to be in joules. They gave us a mass. It's in grams, so you have to make sure that you convert. So 175 grams gets converted into 0.175 kilograms, and they don't make any other mentions, but of course we're dealing with this right here. So C is a constant. It's number 62 in your formula sheet, and it's basically 3 times 10 to the 8th meters per second. The formula is pretty easy to go through. E equals mc squared. Now, I've shown both ways. It's 0.175 times, you can either do 3e to the 8th squared or 3 times 10 to the 8th squared. Don't do both of them. Do one or the other. So times 10 and e are the same thing. But if you do times 10 and e, that's basically saying times 100. And make sure that the squared is applying to the 3 times 10 to the 8th as well. So use an extra parentheses if you have to. But if you punch it into your calculator, and I suggest that you do, you should end up with the energy is equal to 1.6 times 10 to the 16th joules. Not a whole lot to these questions or equations. Just basically always make sure that mass is in kilograms. If it's not, convert it. And remember that you have the constant, 3 times 10 to the 8th. You do have to square that. You're squaring the whole thing, not just the 8. And there you have it. So fairly easy. And hope this has been great. Have a wonderful day.